let's think about a relatively simple rational function. How about that one, 1 over x? What does the graph of this look like? It looks like this. It's got a vertical asymptote at x equals 0, and it's got a horizontal asymptote at y equals 0. And so we have written things like this. We can write, for example, the limit as x goes to infinity of 1 over x is 0. But what does that really mean? Here's the intuitive verbal description. I can make this graph as close as I want to the x-axis where y is 0 by making x big enough. This means I'll use third person. We can make 1 over x as close to 0 as we like by making x sufficiently large. All right, what does that mean? Say I wanted to get within 0.01 units of 0. For example, how big should x be so that f of x equals 1 over x is within 0.01 units of its limiting value, 0. What would that mean? This would mean that 1 over x, well, it's certainly positive. I want to emphasize x is positive. X greater than 0 be. It's certainly positive. I want it to be less than 0.01. I want that to be true. How big should x be? Just solve this inequality for x. How? Take the reciprocal of both sides. And if you take the reciprocal of both sides of an inequality, the inequality changes direction. People sometimes have a hard time with inequalities. I'm using less than signs there. That means x is, yes, 0 is less than 1 over x. So in other words, 1 over x is bigger than 0, positive. And 1 over x is less than 0.01. 1 over x is supposed to be a very small number here. Less than 1/100th. That's equivalent to x itself being a very big number. Bigger than 1 over 0.01, 1 over 100, which is 100. That's how big x needs to be. If you don't believe it, let's try some technology here. Plot the function. What kind of window? We're letting x get big. I probably also want to plot, how about a horizontal line at 0.01? Now, if you pick an ordinary kind of plotting window, you're not going to see what you want to see. Like if I do something like this, you'll see 1 over x, but you won't see the line at 0.01 because it's just too close to the x-axis. So to actually see what we want to see, we need to pick a different plotting window. Oh, how about 0 out to 200? I know x needs to be bigger than 100. I'll make the tick marks, say 20 units apart. And for y, how about 0 to 0.02? This is a very skinny window this way. But of course, on the calculator, it'll get rescaled to look like it's in a square window. You ready? 1, 2, 3, go. All right, here's what the graph looks like. X is going from 0 to 200. These tick marks are 20 units apart. Y is going from 0 to 0.02. There's 0.01. There's our horizontal line at 0.01. Once we get past 100, then the function is below 0.01. If I want to answer this question where I make that number even smaller, how big should X be so that I'm within 0.0001 units of 0? So effectively what I'm trying to do here is everything else is the same, except the 0.01 has become 0.001, 0001. Point 0.0001, yes, is 1/10,000th. This is equivalent to saying X is bigger than 10,000. If I kept the same scale on my calculator, but changed this to 0.0001, it would not work in the scale. You see 1 over X, but you don't see 0.0001 because it's too close to the X-axis on the scale. But if I change my Y-axis to be my Y max to be 0.0002, tick marks that are 0.0001 apart, then I'll see it, hopefully. Did I now change the X? Okay. Yep, thank you. Go out to 20,000. 2,000 units apart. Here we go. There we go. In fact, it looks pretty much the same as the other picture. It's different. It's a different scale, a different window. Looks the same though because of how I changed the scale. And yeah, we're getting below 0.0001 once X is bigger than 10,000. So I could play this game and I could keep making this number smaller and smaller. How do I really prove that the limit is 0? Allow this number to be a positive number that is arbitrarily small. Here's a proof that the limit as X goes to infinity of 1 over X is 0. And again, when I write in infinity with just a plain infinity, I mean plus infinity. Start by saying, let epsilon greater than 0 be given. What? What is that? That's a Greek letter epsilon. What is that? It's technically speaking, it's an arbitrary positive number. Could be large, but what I'm imagining is that it's really, really tiny. Just in my imagination, not of necessity. It could be 10 to the negative 4. It could be 10 to the negative 100. 10 to the 100, that's called a Google, spelled differently than the search engine. Did you know 10 to the 100 is bigger than the number of atoms in the observable universe? And one with 100 zeros after it is a bigger number than the number of atoms in the observable universe. That's a huge number, but it's tiny compared to numbers I can think of. How about 10 to the Google power? A one with the Google zeros after it. You couldn't even write it in the space of the universe. It's called a Googleplex. Not the same as Google's campus in California. Googleplex. Epsilon could be 1 over a Googleplex. 10 to the negative Google power. That's how small it could be. It could be even smaller. I could think of many, many magnitudes of smaller than that. If you know about factorials, I could take a Googleplex and do a Googleplex factorials after it. It's so huge, and that's not even close to infinity, right? Okay, just beyond our imaginations. And epsilon could be 1 over such a huge number. That's how small epsilon could be. But it's not 0, it's positive. Choose X to be bigger than 1 over epsilon. If epsilon's 1 over a Google, then 1 over epsilon is going to be a Google. If epsilon's really tiny, 1 over epsilon is going to be really huge. Then, well, this is also positive, then 0 is less than 1 over x is less than epsilon. That's it. Done. QED. Praise the Lord. PTL. That's all you have to do. What? Really? Yeah, it is. It seems almost too easy, but also hard at the same time, right? It's like both easy and hard. The reason it proves that this limit is 0 is because I've shown that I can make 1 over x arbitrarily close to 0 by making x sufficiently large. And that was what this limit means. Epsilon's an arbitrary positive number, arbitrarily small. I can make it 1 over x arbitrarily close to 0 by making x really, really big. Now realize 1 over x never actually equals 0. Now somebody say, well, isn't 1 over infinity 0? Well, no, because infinity is not a number. In our class, at least. There could be some other more advanced math classes where infinity is a number and 1 over infinity is 0. But not for us. We don't do that. So don't write 1 over infinity equals 0. You need to use this kind of argument. Will I put this on the test? I don't know. Let's keep going. What's another example of something conceivably we should be able to do? How about a proof that the limit as x approaches 0 from the right of 1 over x is plus infinity? Here I am writing equals infinity, even though I said infinity is not a number. Remember, this is just notation to get across an idea that, in this case, the graph gets above any horizontal line as long as x is close enough to 0. What do you do here? Let capital M greater than 0 be given. Epsilon's kind of a standard symbol in math for arbitrarily small number. Capital M, maybe I'll emphasize it's capital, is kind of a standard symbol in math for arbitrarily large number. Always, always, always no, just kind of in this context. People imagine epsilon to be tiny and capital M to be large, humongous maybe, a Google or a Googleplex or something. What's capital M going to represent? Capital M is going to represent my arbitrarily high possible horizontal line that I need to get above. Y equals capital M. What do I need to do? I need to find how close x should be to 0. I'm letting x go to 0 from the right here to make 1 over x bigger than m. It's practically the same kind of idea, except, well, kind of reversed. Let's think about it with an example here. This is not part of the proof. Like, how close to 0 should x be to make 1 over x bigger than 100? Well, if x is 0.01, then 1 over 0.01 is 100. So if x is smaller than 0.01, say half of it, then 1 over that is bigger than 100. In this context, I'm thinking of the 100 as being like the m, and the 0.01 as being like how close to 0 I should be. Choose x greater than 0, so x is less than 1 over capital M. If capital M is really humongous, 1 over capital M is really tiny. X is really close to 0. I maybe didn't need to write it in 2 clauses there. I could have just written one thing like this. Then 1 over x, the function output, is bigger than capital M. Done. QED, PTL. That's all you have to do. It's both easy and hard at the same time. It's hard because it's abstract. It's like, what in the world's going on? It's easy in that you can do it in essentially 3 short sentences. This is making rigorous the idea that I can get above any horizontal line, y equals m, no matter how big m is. As x approaches 0 from the right, this graph will eventually get above it, and I could illustrate it with the graphs in the calculator. If you like this, you might be a pure mathematician. Most of you probably don't like it. You're probably not a pure mathematician, but you should try to understand it anyway. How about another proof? How about a proof that, oh, here's kind of an interesting one. The limit as x goes to infinity of ln of x is infinity. This is the fundamental fact you should know, right? We've mentioned this before. Graphs of logarithms, in this case, log base e, where the base is bigger than 1, they're increasing in concave down. We talked about this last week. They look like maybe they have a horizontal asymptote. I mean, like if you graph y equals common log of x, log base 10 of x in your calculator, and pick a typical kind of window. Oh, like x goes from, say, 0 to maybe even 0 to 100, and y goes from 0 to 5 or so, or maybe negative 5 to 5. It's going to look like it's got a horizontal asymptote. It's going to look like, boy, that's so concave down. It looks like it's not going to get above maybe 3 or 4, but it does. It does get above it. It doesn't have any horizontal asymptotes. Appearances can be deceiving, so you need proof. Yeah, and log base e, natural log, also has no horizontal asymptote. This is going to get above any horizontal line eventually. It's going to get above any line at y equals capital M. By going out far enough, it'll eventually get above that line. Before we do the proof, let's think about an example. Like, what if capital M was 10? Well, let's go to the natural log here. Here's ln of x, ln of x. And I'm also going to graph y equals 10. How big does x need to be to get above y equals 10? When will natural log of x equal 10? X would have to be bigger than e to the 10th, right? E to the 10th. About 22,026. So if I make my window go out to, say, 30,000 in the x direction, that should be good enough. I'll make my tick mark. So how about 10,000 units apart? I want to go up to y equals, say, 15, make these 5 units apart. There's ln of x. And yes, once we get a little past 20,000, it does get above it. It's a little less. Let's go out further so we can see it more clearly. It's going to get above 10 once x is bigger than 22,000 something. So the question is, how do you generalize that idea? It's similar to the start of this one. Let capital M greater than 0 be given. This is our thought about something that is arbitrarily large. How big should we choose x? Choose it to be bigger than e to the capital M power. Then ln of x is bigger than ln of e to the capital M power, but ln of e to the capital M power is capital M. because ln of x and e to the x are inverse functions. Done. QED, PTL. You don't have to put QED or PTL. I just like putting them both because I think it's fun. QED is Latin for quod erat demonstrandum. I think I pronounced it right. It means I demonstrated what I wanted to demonstrate. PTL, of course, is praise the Lord. So that's all you need to do. It's both difficult and easy at the same time. This is leading us to one more kind of example where I'm going to do a proof. This one's a bit trickier, though the limit itself is an easier limit. Limit as, should we do the example from last time? What was it? Limit as x goes to 4. What was it? 3x minus 7? 3x minus 7. I said 3x minus 7, that's a nice linear function. It's continuous everywhere. We can evaluate this limit just by plugging in x equals 4. The answer should be 3 times 4. 12 minus 7 is 5. But let's really prove it. Isn't it good enough just to plug in 4? Not really if you're going to use the true definition of this limit. I need to show that I can make the outputs of this function as close as I like, arbitrarily close to 5, if x is sufficiently close to 4. And technically on either side of 4, because it's a two-sided limit, then that's another thing that makes it a little extra tricky here. So I'm about to show you this proof. It takes practice for this to sink in. This is the trickiest one. So I'm going to let epsilon be given again. Epsilon is my measure of arbitrarily small number, or my symbol for that. I'm imagining it to be a distance to 5. I'm trying to make the output of this function within epsilon units of 5, which means it's going to be between 5 minus epsilon and 5 plus epsilon. I want the outputs to be in this range of y values somewhere by making x sufficiently close to 4. And the question is, how close to 4 does x need to be? Well, in the picture, maybe about this close to 4. If I pick x to be in this picture as close as I've drawn it to 4 here, and now my picture is not accurate because it's a little slanted, but you get the idea. If x is in here somewhere, then f of x is going to be between 5 minus epsilon and 5 plus epsilon. But what are these numbers? The traditional thing to call them is 4 minus delta and 4 plus delta. What's delta? Well, first of all, notice it's a lowercase delta, not a capital delta. It's not like a triangle. What is it? Delta is the measure of sufficiently close to 4. And without going into details about why, I hope it's a little bit intuitive. With a linear function, you want to choose delta to be epsilon over whatever the slope is. Let delta be epsilon over the slope of this function, which is 3. The slope is 3. It's somewhat steep. I need to make delta smaller than epsilon for this to work, is what I'm trying to say. And if it's epsilon over 3, it's going to be small enough. Epsilon's a tiny number. Say delta is also a common symbol for a tiny number. This is positive, though. Suppose x is between 4 minus delta and 4 plus delta. So x is in this tiny little interval somewhere. By the way, people will often write this using absolute value notation. This is equivalent to saying x minus 4 is between negative delta and positive delta, which is equivalent to saying the absolute value of x minus 4 is less than delta. This is a shorthand notation for this that people will commonly use, but this is good enough. What do you want to do? You want to show that the output of the function, f of x here, is within epsilon of 5, between 5 minus epsilon and 5 plus epsilon. How do you do that? Well, one thing you can do is you can replace delta with what it equals. Epsilon over 3. But what else should you do? We need to somehow relate this to f of x. I'd like an f of x in the middle there instead of an x. I'd like 3x minus 7. Right in there. How do I get a 3x minus 7 there? Multiply everything by 3, then subtract 7 from everything. That's how. If you multiply everything by 3, 3 is positive. It doesn't change the direction of the inequalities. I can say this. And this is equivalent to saying, if I do use the distributive property here, 12 minus epsilon is less than 3x is less than 12 plus epsilon, right? 3 times 4 is 12. Epsilon times epsilon over 3 is, or 3 times epsilon over 3 is epsilon, because the 3's canceled. I'm almost there. Now just subtract 7 from everything. It's kind of a run-on sentence here. 12 minus epsilon minus 7 is less than 3x minus 7 is less than 12 plus epsilon minus 7. Big run-on sentence. So simplify. 12 minus 7 is 5. 5 minus epsilon is less than 3x minus 7 is less than 12 or 5 plus epsilon. That does it. We're done. Let's write PTL. What? Why? Because that's f of x. And that's what I wanted to do. I wanted to show the output f of x is in this interval somewhere between 5 minus epsilon and 5 plus epsilon. Now, this might seem like magic. Like, how did I know that was going to work out? Well, experience. I've done this kind of thing before. Would you have to do this on the test? I don't know yet. I got to think about it. It's certainly something that in the meantime you should study. You should think about. The trick that I did of telling you to pick epsilon to be delta to be epsilon over whatever the slope is will always work for linear functions. As long as you don't make any algebra mistakes, it will work out. That wasn't obvious, that I would get an f of x here and 5 minus epsilon, 5 plus epsilon on the other sides. If it's a nonlinear function like x squared, limit as x goes to 4 of x squared is 16, it gets much trickier. So this is about as simple as it gets. But I'm trying to get across to you that these things can be proved. How much I'm testing you on it, I'm not sure yet. It's kind of been dependent on what I've taught the particular class in the particular year. Some classes I've taught this to, and some I haven't taught it so much to, and that has affected how much I've tested people on it. This will not be the only time I say this. I will talk about this more next week. But in the meantime, it is something that in addition to doing your homework this weekend, you should think about.